Hi, I'm Bill Kinney, and this is the second of two videos that I'm making on the Precalculus and Calculus 1 sample placement test for Bethel University in St. Paul, Minnesota. You can probably get benefit out of this for your own placement test at your own school if you don't go to Bethel. In the first video, which I'll put a link to in the upper right corner, I went over the first 15 problems, which were more basic algebra problems. Section 2, which is this video, starting with problem 16, includes algebra still, you can see here with the first problem, but also includes precalculus, includes functions like exponential functions, logarithms, and trigonometric functions as well. All right, so we'll start going through this as I went through the other one before. I will solve the problem fairly quickly with some brief explanations, but you should also realize that if you want to do well in these classes, you should understand things more deeply. We expect at Bethel for people to do well in Section 1 if they're going to place into precalculus, and we expect people who are in Calculus 1 to do well in both Sections 1 and Section 2. So the first problem here, number 16, is to find the product of two things, two polynomials, a linear function and a quadratic function. This is a binomial, it's got two terms, and this thing here is a trinomial, it's got three terms. I cannot use the FOIL method, first, outside, inside, last. Instead, I need to use the fact that the distributive property will ultimately say that I can take each term in the binomial, the x and the negative 3, individually and multiply times each term in the trinomial. So, for example, first of all, x times x is x cubed. X times the next term here, 3x, is plus 3x squared. And then x times 5 is plus 5x. Now do the same kind of thing with the negative 3 here. And line up the like terms vertically. That'll help you avoid mistakes. Minus 3 times x squared is negative 3x squared. Line it up under the other x squared term, and you see those are going to cancel. Negative 3 times 3x is minus 9x. And finally, negative 3 times 5 is negative 15. Now add these, which means here you're going to subtract x cubed plus 0, so to speak, is just x cubed. 3x squared minus 3x squared is 0x squared, or just a 0. 5x minus 9x is minus 4x, and then 0 minus 15 is minus 15. Then you put those together and see that the answer is choice B, right there. Okay? Sometimes you could see perhaps the answer will not be given. But in this case, this is the correct answer, and I encourage you to check that on your own. In fact, I'd encourage you, as you're watching this video, to do the problems before I do. Pause the video, try the problems on your own, and then check and see what I do, especially if you are not sure what the answer is. So that's the first problem of Section 2, again, number 16 of the overall exam. On to the second problem of Section 2, which is number 17 of the overall exam. Simplify this fraction that you see here. And notice the numerator involves the product of two things, quantity squared. I need the following property, which I talked about in the last video. A times b to the c power is a to the c power times b to the c power. Treat the 2x squared like the a, the square root of x plus 2 like the b, and the 2 there like the c. Giving me 2x squared, quantity squared, times the square root of x plus 2, quantity squared, all over x cubed. I will need the same property right here. Treat the 2 like the a, and the x squared like the b, and 2 like the c, giving me 2 squared, which is 4, times x squared squared, which is indeed x to the 4th. Now, 2 has the pretty cool property that 2 plus 2 and 2 times 2 equal each other. They both equal 4. But you do want to think of multiplying the exponents there. You want to think of it in terms of the following property. A to the b all to the c power is a to the b times c. The situation where you add exponents is when you have like a to the b times a to the c. There you would add exponents. You'd get a to the b plus c power. And you can reason these all out like I did in the last video, at least when the exponents are positive integers, whole numbers, by thinking about the meaning of exponentiation in terms of repeated multiplication. Square root of x plus 2 squared makes the square root go away. They're inverse functions. You get x plus 2. Make sure you use parentheses. It would be a common mistake here to not include the parentheses, but you do want to make sure you're multiplying this thing times this whole thing Does mean you're going to need to use the distributive property on top, at least after you cancel some x's here. This x cubed cancels with the x to the fourth, leaving an x to the first on top, or just x. 4x gets distributed through the parentheses, divided by 1. I don't have to include it when I divide by 1. 4x times x is 4x squared. 4x times 2 is plus 8x. And that is also choice B. Okay? On to the next problem. We have a compound inequality here. You see a less than or equal to there and a less than there. Right? You have a linear expression, linear function, if you will, in the middle. That's good. That helps us be able to do this fairly easily. You'd want to start by, you're trying to isolate the x in the middle. Okay? So you want to get rid of that plus 1 there. So start by subtracting 1 from everything. Don't say from both sides, because both implies 2. Say subtract 1 from everything. That'll cancel the plus 1 there. Negative 2 minus 1 is negative 3. Keep the inequality in the same direction. Is less than or equal to 2x plus 0, or just 2x. And then 5 minus 1 is 4. When you add or subtract a number from everything in inequalities, the inequalities stay the same direction. Isolate x now by dividing everything by 2. Divide everything by 2. 2 is a positive number. Therefore, the inequalities continue to stay the same direction. If I had multiplied by a negative number, maybe because this had been negative 2x, then the inequalities would have changed direction. Is this an option? Yes, it's option A. Okay? By the way, the same numbers, negative 3/2 and 2, appear in option C, but the direction there doesn't make any sense. Okay? 2, for example, is not less than negative 3/2. This doesn't make any sense. Option A is the answer. Here we're simplifying a fraction to a power. That power is a negative 1/3 power. Well, the first thing you should do is think about what it means to raise a number to a negative power. Or say a fraction even to a negative power. So for example, 4/3 to the negative 2 power, by definition means 1/4 to the positive 2 power. By definition. It's nothing magical there. It's a definition. Why is it a definition? It's because it makes rules of exponents work even when your exponents are negative. That's why it's done. What does that equal? That equals 1/, well, 4/3 squared is 4 squared over 3 squared. That's 16/9. You could also multiply the top and the bottom of this fraction by 3 squared and write it as 3 squared over 4 squared, which is 9/16 in the end. And this, by the way, is the same as 3/4 quantity squared, which is worth noting here because I could have also started this problem by jumping from here to here. And that's going to be what I do here. So that's why I went through all that. Take this expression, flip the fraction inside, and change the exponent to the corresponding positive exponent. That is a property of exponents. And I illustrated it with a simpler example over there. So flip the fraction, 27y to the 6th over 8x cubed. Now it gets raised to the positive 1/3 power. And just like we had a few problems ago, this power now can get distributed, so to speak, through all the factors, including factors in the bottom of the fraction. But now it looks worse. It it's actually better. We can now simplify this pretty quickly. This is a 1/3 here. What does it mean to raise something to the 1/3 power? What is 8 to the 1/3, for example? Well, that's something to remember as well. That's by definition the cube root of 8. That's, again, a definition, nothing magical. It's a definition made so that properties of exponents continue to hold even when your exponents are fractions. Now, what is the cube root of 8? It's a positive number. We're dealing with just real numbers here, not complex numbers in this case, whose cube is 8, which is 2. And by the way, the cube root of negative 8 would be negative 2. We're talking about real numbers. In that case, negative 2 is a real number whose cube is negative 8. You can have other cube roots if you bring complex numbers into play, which we do not want to do here. And that's going to be another thing I mention later in the video in other problems. How about 27 to the 1/3? The cube root of 27, that's 3. What do you do here? You multiply the exponents. I mentioned that property as well. And 6 times 1/3 is 2. Also multiply the exponents there. 3 times 1/3 is 1. The answer is choice C. Okay, so that's a bit of a tricky problem. On to number 20 of the overall exam. By the way, we'll be done when we get to number 32, or when we get done with number 32. Here you can see we've got a function. Now we started to get into what you might call true precalculus stuff, functions. Thinking about their graphs and intercepts, thinking about evaluating them like this, even when they're piecewise defined. And then particular functions include, again, exponential, logarithms, and trigonometric functions. You have to understand function notation. When you look at this expression right here, you want to say f of x. It's a common mistake to think that this is like f times x or something. No, f is not a number. F is just the name of the function. X is a number. I'm plugging the number in. This notation means I'm plugging the number into the function to get an output. X is the input of the function, y is the output. You don't see a y here, but I could certainly write a y if I wanted to. That's fine, okay? And with a piecewise function like this, you've got cases. And for the given input, negative 1/3 in this case, you've got to decide which case is it in. Inequalities sometimes confuse people. You've got to be careful. It's the second case. Negative 1/3 is greater than negative 1. On a number line, negative 1/3 is to the right of negative 1. It is therefore greater than negative 1. So it fits the second case. So you use the second formula. You replace x with the input, negative 1/3. Then you get negative 1 plus 1 is 0. Negative 1/3 is a root of this function, this piecewise function. If you try graphing this function, you get a graph in two pieces, one with a slope of 6 over here and one with a slope of 3 here. And there probably looks like there'd probably be a discontinuity at negative 1. The second piece is going to intersect the x-axis at x equals negative 1/3. That's what's going to happen. You're going to get a picture something like that. The answer is 0, choice B. '21 is about function composition. F of g of x is what you say. F of g of x. Sometimes written, you should realize, as f circle g of x, or like my high school teacher used to say, fog of x. That's just a joke. F circle g, the circle's not an O. The circle really represents, it's not a geometric object either, it just represents a symbol to say we're to combine these two functions, f and g, to get a new function. It's kind of like a plus or a times symbol, or a subtraction or a division symbol, okay? But with functions now instead of numbers. It's just letting you know. Sometimes you'll see it like this. But for calculus, it's important to think of g of x as the inner function, the inside function, and f as the outer function, the outside function. And what you do is, well, first replace g of x with its formula, 2x plus 5. And then, this is real key that you understand this, really important for calculus, and pre-calculus for that matter. So you need to take the formula for f and replace whatever you see here, no matter how crazy looking it is. Replace x with that thing. Say that again. Whatever is here, no matter how weird it looks, it's only a little bit weird this time, 2x plus 5, but it can be a lot weirder actually. Replace x with that thing. This is the input for the function. To get the output, I multiply by 3, because the function represents multiplication by 3. Multiplying an input by 3 to get an output. Make sure you use parentheses. And maybe for extra emphasis, put a dot in there to emphasize your multiplying. And now use the distributive property. Again, f is not a number. It's just the name of the function. You don't distribute here, but you do distribute here. 3 times 2x is 6x, 3 times 5 is 15, 6x plus 15 is the expression that defines the formula for this composition. This is f of g of x. In calculus, actually, it's useful to decompose functions, although in this example that wouldn't be done. But there's certain situations in calculus where you actually go the other direction with this kind of problem. You reverse the process and try to find f and g when you know f of g of x. This one is about inverse functions. Fortunately, our original function is linear. That makes finding the inverse function fairly easy. What is the inverse function all about? Is it like inverses of numbers? You know, 4 to the negative 1 power is the multiplicative inverse of 4. By definition, it's 1/4. The thing you multiply 4 by to get 1. Does that mean f inverse of x is the 1 over this? That? No, it does not. It's not that. It's maybe unfortunate notation, because it makes you think you're raising f to the negative 1 power, but you're not. If you were raising the output of f to the negative 1 power, you'd use parentheses like this. That would represent 1 over f of x. But it's standard notation that when we write this, we do not mean this. That's unfortunate, but that's the way things are. So how do you find the inverse function? Well, it's like you're trying to solve for the independent variable in terms of the dependent variable. Y is the dependent variable, x is the independent variable here. Solve for x in terms of y. Why might you want to do that? Because it allows you to solve really infinitely many algebra problems all at once. For an arbitrary y, what is x? That's a pretty cool thing. Inverse functions are pretty cool, I think. So we want to isolate x. So add 1 to both sides here. Y plus 1 will equal 3x. Divide both sides by 3. 3 divided by 3 here is 1. 1 times x is x. You get x equals y plus 1 over 3. And that is the inverse function. F inverse of y is y plus 1 over 3. Or if you prefer, you could break that a fraction apart and write it as 1/3 y plus 1/3. But wait a minute, I don't see any y's in these answers. Okay, so here's where we do the swapping. The swapping is not absolutely necessary. And in fact, if your variables mean something, like if x were the number of items you made and y was your profit, you would not want to swap in the inverse function. That would be a bad idea. The swapping is essentially done for 2 reasons. Switch the f and the x and the y around here. One reason is that we just typically like x as the independent variable. A second better reason is that if you graph both the original function here and the inverse function here on the same set of axes, with the x-axis horizontal and the y-axis vertical, and treating the x-axis as your input axis, The graphs will have a nice property. They'll be reflections of each other across the line y equals x. There. In fact, I can make a quick graph right now. 3x minus 1 is going to look something about like this. That's the graph of f. And the inverse functions graph, x plus 1 over 3, is going to look something about like this. That'll be f inverse. And they are reflections of each other across that line. If you turn your head sideways at a 45-degree angle, you can see their mirror reflections. Okay? But again, if your variables mean something, don't swap. And you'd want to graph them on separate axes that are labeled differently. And in the abstract, you don't need to swap. Functions are, the letters don't matter. What matters is the operation, or operations. In this case, take a number, multiply by 3, then subtract 1. In this case, take a number, add 1, then divide by 3. It's the operations that matter, not the letters. In fact, I could even write g of z equals 3z minus 1, and I'd say f and g are the exact same function, even though I'm using different letters. These kinds of subtle things can cause confusion. And what you need to dispel the confusion is somebody, your teacher, to tell you these things, to make it clear. All right, here we're after x-intercepts of the graph of a function that is a quadratic. Where does it cross the horizontal x-axis? We need to set f of x equal to 0 and solve for x. Effectively, set y equal to 0 because you're going to cross the x-axis when y is 0. With quadratics, you can either try to factor or use the quadratic formula. The quadratic formula always works. Technically, factoring always works too, but it's not always very easy. And in fact, if it was a very difficult problem, you'd have to use the quadratic formula to help you figure out how to factor it in the first place. So it kind of just use the quadratic formula in that case. Okay? With higher degree polynomials like cubics and quartics and quintics, and I guess a 6th degree polynomial would be a hextic, it's harder, okay? And you have to be very lucky to be able to factor. I mean, in some college algebra books, they give you lucky problems where you can factor them, so to speak. But the arbitrary hextic can't be factored, okay, by anybody, including the smartest people in the world, because it can be even shown it's not possible to do so in any ordinary sense of the word. You can do so in a theoretical sense, but not in an ordinary sense, where you can actually find expressions representing the numbers that are nice and simple. All right, this one can be factored. We got lucky. You got to think about reversing the FOIL process. First, outside, inside, last. Certainly when the coefficient of x squared is 1, like it is here, that's good because you can just put x's in both of these spots. First times first will be x squared. You want last times last to be 2, the constant term. Probably the answers are either going to be plus 1 and plus 2 or minus 1 and minus 2. Could they be fractions? Well, they won't be. You're always hoping that, okay? The outside and inside products have to add to negative 3x, so they better be minus signs. Minus 1 and minus 2? Or should I do it the other order? No, it doesn't matter. Multiplication is commutative. Some people are tempted to say this means x is negative 1 or negative 2, but that would be wrong. The answer is x is 1 or 2, which is not given. The answer here is not given. This is a not given one. If the product of two things equals 0, that means one or the other must be 0. So either x minus 1 is 0 or x minus 2 is 0, meaning x is either 1 or 2. And both of those numbers are solutions. You can check in the original equation. The solution set, using curly braces to specify a set, consists of the two numbers 1 and 2. Okay? But that's not given here. So the answer to the problem is not given. I think it's worth using the quadratic formula here to review that. That's definitely a very useful thing. Even in higher level math, for example, I teach differential equations a lot, and we use the quadratic formula all the time in there. especially in the situations where we're trying to find what are called bifurcations. It's a pretty interesting subject. So what's the a, the b, and the c here? A is the coefficient of x squared, which is 1. B is -3, the coefficient of x, and c is the constant term 2. The formula says negative b plus or minus square root of b squared minus 4ac all over 2a. Negative of -3 is +3. -3 squared is 9. 4 times 1 times 2 is 8. 2 times 1 is 2. 9 minus 8 is 1. Square root of 1 is 1. 3 plus or minus 1 over 2. 3 plus 1 over 2 is going to be 2. 3 minus 1 over 2 is going to be 1. Not given is the final answer. Again, the last problem is going to be number 32. Number 24 of the second section of the overall test. More functions. And this particular problem is really important for calculus. If you take a Calculus 1 course first semester, you'll be doing this kind of calculation all the time when you're computing limits of certain situations that give you derivatives. It's a really important kind of calculation for that. And I emphasize once again, f is not a number. It's the name of the function. I could have called it g, I could have called it h. Its name doesn't matter, but it is a function. So when you see f of x plus h, take that entire expression, just like I said a few minutes ago, and replace x by it in the formula for the function. So I get 2 times the quantity x plus h, quantity squared, minus 5. That is f of x plus h. It's a common mistake to think this is maybe f of x plus f of h or something. There you'd be treating f like a number, but no, it's not a number. There's no distributive property to use here. Minus f of x minus this expression, use parentheses. I'm subtracting the whole thing. The minus sign can get distributed through the parentheses because what you're really doing is you're really adding -1 times this, and then the -1 can go through. And that's going to mean, like with the 5, the constant term, you have a minus 5, really plus 5. Negative of -5 is plus 5. -5 plus 5 is 0. This cancels with this, ultimately. Another common mistake is to forget, oh, I need to use FOIL here. X plus h squared is x plus h times itself. And that does not equal x squared plus h squared. There's no corresponding property when you have a sum there to take this 2 and put it in both spots. Those are part of the answer, but when you FOIL, you get another term involved. X times x is x squared. X times h is xh. But inside times inside is also xh. You get plus 2xh. And then last times last is h squared. And then we have also minus 2x squared from this part here. Distribute this 2 through. You'll get a 2x squared minus 2x squared. Those will cancel to 0, which you don't have to write. You multiply these by 2, you get 4xh plus 2h squared. And that is option D. You can switch the order because addition is commutative. Okay? Very tricky problem for many people, okay? But really important if you want to do well in Calculus 1. And in Precalculus 2, you'll get practice at this kind of thing because in Precalculus, you are, in a sense, getting ready for calculus. So they practice this kind of thing. Domain of a function. We are implicitly assuming both the input and output are real numbers here, not imaginary and not complex numbers. Therefore, when you see a square root, you want the input to be greater than or equal to 0. If you see a cube root, then it doesn't matter. Cube roots of negative numbers, when we're dealing only with real numbers, do exist. The cube root of -8 is -2. But with square roots, We want the input to be greater than or equal to 0 in Calculus 1, unless your teacher decides to do imaginary and complex numbers. Solve for x. Subtract 2 from both sides. With addition and subtraction, we do not change the direction of the inequality. With multiplication or division by a positive number, you also do not change the direction of the inequality. Again, if this had been a -3 and I had divided both sides by -3, then the inequality would have changed to a less than or equal to. At least when you have the x on the left side. By the way, just realize x being greater than or equal to -2/3 is equivalent to x being, to -2/3 being less than or equal to x. These mean the same thing. And a number line, they're all the numbers to the right of -2/3, including -2/3, because it's not a strict inequality. That's what this domain is. And this is a useful thing because it would help you graph the function on a graphing calculator, for example, to know what kind of window to choose. All right, it's 4 options that are none of which are not given. It must be one of the answers. Careful here. It's option C, which is different than option A. Okay? And option A is also not the same thing as that. All right. So 25, the answer is C. In 26, we're solving an exponential equation. In general, to solve exponential equations, you have to use logarithms, and to get a numerical answer, you have to use your calculator, typically. Here, these are nice answers. There is also no solution option, which is not the same as not given. It means there is no solution to the equation. So we must be able to figure this out without logarithms, perhaps. Well, you could use logarithms, though. If you did, you'd use log base 5, and you just have to think about it carefully without a calculator. But another option here is to realize, hey, 125, that's a nice power of 5. It's 5 to the 3rd power, 5 times 5 times 5. And then I can multiply these exponents. This is a 5 here, by the way. Sorry. Got goofed up there. Multiply those exponents. I get 5 to the 3 times this entire thing. Imagine parentheses in your head. 9n plus 15. The function whose output is 5 to the x is what's called a one-to-one function. Distinct inputs give distinct outputs. Said another way, if you get the same output, the inputs must have been the same. So if this equals this, then the input, -n, well, if you just think of it as 5 to the x, -n and 9n to the plus 15 must be the same. -n must equal 9n plus 15. Solve for n. Add n to both sides. Subtract 15 from both sides. -15 equals 10n. So n is -15 divided by 10, which is -3/2. -1.5, which is an option, option A. Probably want to check this. Go back to the original equation. 5 to the -n is going to be 5 to the 3/2. Well, you get the same thing when you plug -3/2 in for n there and simplify. 125 to the 3 times -3/2 plus 5. That's -9/2 plus 5. 5 is the same as 10/2. This is 125 to the 1/2. Same as 5 cubed to the 1/2. Multiply the exponents. This is the same as 5 to the 3/2. It does work. There is an at least a couple problems about logarithms on this test that we will come to here in a few minutes. But I think I would like to mention how to think about this with logarithms. It could be thought of as with logarithms. I think there's no other problem where it's going to be like what I'm about to show you here. You could take the log base 5 of both sides. And then if you know properties of logarithms, this can be easily simplified. One property of logarithms, and I'm assuming you know them here or you've learned them at some point, is that log of something to a power, the power can be brought up in front. This should ring a bell, hopefully. You've studied logarithms before. If you haven't, then, well, this is new to you. Same thing here, the power can be brought out in front, and I would use parentheses here. Yes, definitely use parentheses. Then you got to evaluate these logs. What is log base 5 of 5? It's the number 5 must be raised to get 5. That's what it means. The number, whatever the base is here, must be raised to in order to get whatever's here. 5's got to be raised to the first power to get 5. This whole thing is a 1. For this thing, what do you have to raise 5 to get 125? The base is 5, the number there is 125. This whole thing represents the number to raise 5 to get 125. 3. Right? 5 cubed is 125. Distribute the 3 through here, you get 9n plus 15. You get the exact same equation that I erased already before. I think. Yep, okay, I erased it. Negative n times 1 is negative n equals 9n plus 15. Therefore, 10n equals negative 15, and n is negative 15 tenths, which is negative 3 halves. Same answer. Take a breath here. Here we are solving a logarithmic equation for a variable, for an unknown. Instead of solving by taking the log of both sides, you exponentiate both sides. Or, thought another way, you think about what the logarithm means. This whole symbol represents the number to raise 5 to get x. Therefore, it equals negative. If it equals negative 2, that means 5 to the negative 2 equals x. Should I say that again? This whole symbol, by definition, is nothing magical. By definition, this whole symbol represents the number to raise the base to 5 to get the input, x. Therefore, x must be 5 to the negative 2 power, because we're saying this equals negative 2. Which is the same as 1 over 5 to the positive 2, which is the same as 1/25. X is 1/25. Option A. Another way to think of it is to exponentiate both sides. 5 to the log base 5 of x equals 5 to the negative 2, which is the 1/25. And then 5 to the x and log base 5 of x are inverse functions. This simplifies to x. They undo each other. A is the answer. Getting close here to being done. 32 is the last problem. Here we're doing a purely symbolic problem using properties of logarithms. Before we brought the power out in front, here the number is in front, we want to bring it into the power. That's a property of logs. When you write log, by the way, it means log base 10. Typically, at least, there's higher math where they actually mean log base e, even when they write log instead of ln. But here we mean log base 10, but the base doesn't really matter. The properties of log are the same. Now you've got a log of something plus a log of something else. There's another property that says that's the same as the log of the product of these two things. The proof of that is not difficult, but I don't want to take the time to do it. Let's just think about it with an example. Log of 100 plus log of 1,000, log being log base 10, is the same as 2 plus 3, right? Because it's log base 10. This is the number you must raise 10 to get 100, which is 2. This is the number you must raise 10 to get 1,000, which is 3. This is 5. That does equal log of 100 times 1,000. 10 squared times 10 to the third is 10 to the fifth, or 100,000. Okay, so it works with that example at least, and you can try other examples. It's not a proof because it's thinking about particular examples. But the logic of the proof involves similar kinds of ideas. Okay. Anyway, the answer here is choice B, which is not the same as, I mean, don't get confused. Okay, I mean, it definitely doesn't look like the other ones. This is a little confusing notation here. I would take this to mean this, which is technically different than that. So just be aware of that kind of thing as well. I think people should use parentheses, with both logarithms and trig functions, I think people should use parentheses in more clear ways. And use powers with more clear ways as well. Convert 30 degrees to radians. Maybe you haven't memorized. It's pi over 6. There's the answer. Maybe you don't have it memorized. How could you figure it out if you don't have it memorized? Well, 30 degrees is to, say, 360 degrees. As to its radian measure, call it x, is to 2 pi. 360 degrees all the way around a circle. Same as 2 pi radians. You could also just think of a half turn around a circle. 30 degrees is to 180 degrees as x is to pi. These two things are equivalent. You can think of it either way. And therefore, if you take this one, for example, and multiply both sides by pi, x is pi times 30 over 180, which reduces to 1/6. This is pi over 6. Okay? Or you could just have it memorized. So we're talking about degree measure and radian measure of angles here. Something you should know if you want to be in calculus. C is the answer. Pi over 3 is double that, is 60 degrees. Pi over 12 is half that, that would be 15 degrees. And I don't know how many degrees that is. Okay, and 30 over pi, I don't know, 8 or 9 something radians, which would be over 360 degrees. Simplify the trigonometric expression. You need to know the definition of secant and cotangent. Secant, by definition, is 1 over cosine. It's the reciprocal of the cosine function. I'm going to use parentheses here because I think that's a good idea. Which is not the same as the inverse cosine function. It's not the same as this. That's an unfortunate notation again. It's probably better to call this arc cosine, as some people do, to avoid that confusion. These mean the same thing. 1 over cosine of x, this does not equal. This is cosine of x all to the negative 1 power. That's the same as what we call secant of x. Okay? If you've never seen this before, it's pretty confusing, I know. Cotangent of x is cosine of x divided by sine of x. Same as the reciprocal of the tangent function. Distribute this through the parentheses. Distributive property. When you multiply this times that, the cosine of x is canceled to leave you 1. 1 over sine of x, by definition, is cosecant of x. It's kind of funny. The s's go with the c's. Secant of x is 1 over cosine of x. 1 over sine of x is cosecant of x. It's confusing. The cos get swapped. And then 1 over cosine of x times sine of x is sine of x divided by cosine of x is tangent of x. That's probably the option we're after, and yes, that is option B. I think it's very good in this problem that they didn't give you the option of not given. People make a mistake. They're not going to be. It's not going to be clear what the answer is. It's got to be one of these four, and choice B is the answer. 2 more problems. Oh, this one should be easy, I hope. The graph over there on the right corresponds to which of these functions? You're supposed to do this exam without a calculator. You got to have knowledge of what graphs look like. Looks like a logarithm, okay, right? That kind of shape is your typical kind of logarithm shape. So it looks like it should be B or C. Which one is it? This one takes, well, by the way, ln means log base e, or e is the special number that's approximately 2.71828. It's called the natural logarithm, or in French I think it's the log natural or something like that. This one takes the ln of x graph and shifts it to the right by 1 when you subtract 1. This one takes the ln of x graph and shifts it to the left by 1. That looks like a shift to the right. The ordinary ln of x graph would look like that. It's a shift to the right. It's choice C. These things are exponential functions. If I were to graph them quickly, the graph of this one, it's going to look something about like that. Let's go with the negative sign. And you've got a negative sign there too. This is the same as negative 2e to the negative x. The graph of that one is going to look more like this. Okay? And the shape of that kind of looks like that, but this one's defined for all x's, where this is only defined when x is bigger than 1. For the domain of that function. That's just something to know. One more problem, and it's a trig problem. Solving a trig equation. This also, if you're doing it without a calculator, involves some memorization. But first, before the memorization, isolate sine of t on both sides. So add 5 to both sides first. That will give you 2 sine of t, and again, I'll use parentheses here because I think that's a good idea. Negative 5 plus 5 is 0. Negative 4 plus 5 is 1. Now divide both sides by 2. Sine of t equals 1/2. Now, if you had a calculator, you could say t is the inverse sine of 1/2, or arcsine of 1/2, and you'd get, with your calculator, an answer of pi over 6. But that's not the answer to the problem. You can see all options give you 2 answers. We're after all solutions in this interval. I find it best, well, you can think about it 2 ways. You can either try to draw the graph of the sine function and guess where it's crossing y equals 1/2. I prefer typically to think of it in terms of the unit circle definition. Pretend this is the unit circle centered at the origin with a radius of 1. We're after angles whose sine is 1/2. The sine of t, thinking of t as an angle in radians, is the second coordinate of the point where this crosses the unit circle. So for example, if your angle, well, let's say your angle is like this. This is t. Then the second coordinate of that is sine t. The first coordinate is cosine t. This is the unit circle. Radius of 1. So we're after an angle in radians where the second coordinate of that point is 1/2. Let me use a different color. Second coordinate of 1/2. 1/2 is right about there. we're after this angle and this one. This one is pi over 6, and that's just something to remember. This one, it should look like, from symmetry, yeah, it's true, it's going to be pi minus pi over 6. Pi minus pi over 6 is 6 pi minus pi over 6, getting a common denominator, which is 5 pi over 6. Oops. 5 pi over 6. But we also have pi over 6. There are two answers. And therefore the answer to the problem is choice A. Okay? That is the last problem. Thank you for watching.